Hi everyone, so today we begin our unit in trigonometry, and where can we start? Triangles, of course, since they're the base of trigonometry. And today is just going to be a review. I'm hoping that everyone goes through this lesson and they're like, got it, thanks for the refresher, but I already knew all of that. And if you are looking at the content in the lesson and feel like I'm good, obviously feel free to move on to the next lesson. So the first thing we're going to discuss is the Pythagorean theorem, which probably learned in Algebra I. So the Pythagorean theorem says that if you have a right triangle, then a squared plus b squared is equal to c squared, where a and b are the sides of the triangle, the two that are adjacent to the right angle, and c is your hypotenuse, the side that's across from the right angle. So what I want to do is look at this next slide. It's got 4 triangles on it, and they have 4 different lengths. I do need to add in, well, I don't have to add in the right angle. Actually, I'm not going to add in the right angle. You should be able to tell me where the right angle is based on those side lengths. Remember, if the right angle is the largest angle in a right triangle, then the longest side has to be opposite from it. So the longest side in these triangles would be the right angle if it is a right angle. So what I want you to do is use the Pythagorean theorem and decide if these are or are not right triangles. Pause the video and then come back when you're ready. Welcome back. So hopefully you can check through your results and see that there was actually only one triangle that is not a right triangle, and that would be the first one. Whenever you put the side lengths into the Pythagorean theorem, you get a statement that's not true because 100 does not equal 81. But whenever you do the other ones, you see that in the second one, 169 equals 169, so you're good. In the third, 100 is 100, and in the fourth, 25 is 25. So all of those are right triangles. Now what we want to do is find the missing side length for each of these triangles. In the first one, I noticed that the hypotenuse is missing, so I'm going to give it a variable x, and then I'm going to do the Pythagorean theorem to set up an equation. So I have 4 squared plus 8 squared is equal to the hypotenuse squared, which I named x. 4 squared is 16, 8 squared is 64. And so when I add those together, I end up with 80 equals x squared. And now I need to take the square root. Now since I'm solving an equation, you have to consider the plus or the minus sign. Now the square root of 80, I believe, can simplify. I'll come off to the side to do that. 80 is equal to 16 times 5, and the square root of 16 is 4. So I end up with x could be plus or minus 4 root 5. But since I'm looking at the side length of a triangle, it's not possible for this side length to be negative. So the only solution for my x is going to be 4 times the square root of 5. Now in the next one, I am looking for a side length, and it is not the hypotenuse, it's one of the sides. So I'm still going to call it x, but when I set this up, it's going to be 9 squared plus x squared equals 41 squared. So 9 squared is 81. 41 squared, I don't know, so I'm going to tap that out on my calculator quickly. I get 1,681. So this is actually going to be very convenient. Now to solve for x squared, I got to subtract the 81. Giving me 1,600. Press the wrong button. When I take my square root of both sides, you end up with 40. Plus or minus again. But of course, I can't have a negative side length, so this side is going to be 40. Now, all the triangles we've looked at so far, not all of them, but this one and a couple on the last slide, this is called a Pythagorean triple. The 9, 40, 41 ratio is a Pythagorean triple because you have a right triangle with 3 integer sides. I believe we had a 3, 4, 5 Pythagorean triple, and a 6, 8, 10 Pythagorean triple on the last side, but there's a lot of different combinations that you're probably going to see come up pretty frequently. Okay, so now we're going to look at special right triangles. There's two that we are going to use a lot in this whole unit. The first one's a 45, 45, 90 triangle. So that means that you've got 45 degrees for my angles, my two acute angles, and a 90-degree angle, of course. Now, we know that this is an isosceles triangle because if you have 45-degree angle measures, then the sides that are across from them have to be the same. But we also know that they have a special ratio. So if the side lengths have to be the same, let's call it x, then the hypotenuse is always the side length times the square root of 2. So you always have these ratios going on. And another triangle that I will draw a lot is a 45-degree angle. And I will set the side length to 1 and 1. And then the hypotenuse is just 1 times the square root of 2, or the square root of 2. So notice both of the triangles have the same ratios. One kind of sets the side length to x, and one sets it to 1. Let's see, I need my other one. Oh, I see. When I take, there we go. There it is. The next special right triangle is a 30, 60, 90 triangle. So here, you've got a 30-degree angle and a 60-degree angle, and then my 90-degree angle. So here, if you have, across from the 30-degree angle, this will be the shortest side. Since it's across from the 30 degrees, and 30 degrees is the smallest angle. Across from the 60 degrees is the long side. And then, of course, across from the 90-degree angle is the hypotenuse. Now, don't get confused with me naming the long side, long side, because the hypotenuse, of course, should be the longest side of the triangle. Now, if you have a short side, let's say it is x units long, well, then the long side will be equal to the short side times the square root of 3, and the hypotenuse will be equal to the short side times 2, so 2 times x. So really, this short side, if you can figure out what this short side is right here, the long side, you just multiply by the square root of 3, hypotenuse, you multiply by 2. So that short side is kind of the driver here in a 30, 60, 90 triangle. And these ratios will always hold. So if you were to write a little reference angle, 30, 60, 90, if you set the short side to 1, then the 60-degree side will be the square root of 3, and the hypotenuse is going to have a length of 2. And those ratios will always hold. So what we want to do now is we want to find the missing lengths of the following triangles. So in the first one, I've got a 30, 60, 90 triangle, and it looks like my short side is 2 because it's across from the 30 degrees. So this 2 right here is my short side. So that means across from the 60-degree angle is the long side. It's going to be equal to the short side times the square root of 3. And the hypotenuse, u, is going to be equal to 2 times the short side. So I'll end up with a 4. So 4 is my u, and v is 2 times the square root of 3. So that's probably going to be the easiest example where I'm just given the short side. Here in the next example, I've got a 45, 45, 90 triangle. Now, I'm given one of my side lengths because it's across from the 45-degree angle. So that means that my other side is going to be equal, since I know these two side lengths have to be the same, since 45 and 45 are the same. So I know my y is 3 times the square root of 2. Now my hypotenuse here, which is x, is always going to be equal to the side length, which is 3 root 2, times the square root of 2. Well, I know if I take the square root of 2 times the square root of 2, that's the square root of 4, and the square root of 4 is just 2. So I end up with 3 times 2, which is 6. So that's how we're doing those two problems. All right, so now what we have here are two more examples where we're finding the missing side lengths. What I think you guys should do is pause the video and give these two a try, and then come back when you're done and check your answers. Okay, so go ahead and check your answers for x and y in both triangles. They're both 30, 60, 90 triangles, but in the first one I gave you the long side, and the second triangle I gave you the hypotenuse. So in the first one, hopefully you noticed that since you have the long side is always equal to the short side times the square root of 3. Well, this square root of 3 is beautiful because that means this right here has to be equal to my short side, y. And so once I have y set as 5, I know the hypotenuse is just equal to the short side times 2, giving me 10. It would have been a little more complicated if that square root of 3 hadn't been there, and I think we're going to do one of those here in a little bit. So now let's take a look at the next one. Here I gave you the hypotenuse. Well, you know the hypotenuse is always equal to 2 times whatever the short side is. And I don't want to use an x necessarily because it doesn't line up here. I'm just going to put 2 times SS, short side. Well, that means the short side has to be equal to 8. And my short side in this triangle is y. Once I have that set, I know that the long side is equal to the short side, which I've decided is 8, times the square root of 3. So that's how I set the x. Let's take a look at two more triangles, which are going to be a little complicated. So we'll do these together. Not terrible, just a little different. So here what I've got is, well, no, this first one's really easy. The second one, I've got this short side given to me again. So that 8 is across from the 30. So this is going to be super easy. Short side times the square root of 3 is going to be the long side. So that's my v. And then my hypotenuse is equal to the short side times 2, giving me 16. Notice, pretty sure these are the same two triangles that I just had. Can't get them in the same frame. Yep. Same triangles, just different rotation on them, but same side lengths. All right, let's look at this last one here on this slide. So here, I've been given the hypotenuse. What I want to do is I want to draw the 45, 45, 90 triangle. With my ratios here. So some people will put the x's, some people will just have the 1, 1, square root of 2, but some people like to have the x's on there, which is fine. So what this means is that this is the hypotenuse and this is the hypotenuse. So 2 root 6 is equal to whatever the side length is, I'm going to call it x, times the square root of 2. So if I solve for this value right here, I will know what the side length is of this triangle. And to get that by itself, I need to divide by the square root of 2. So I know that when I'm dividing square roots, since they have the same index for the radical, I can just divide what's on the inside, and 6 divided by 2 is 3. So the 2 is just hanging out, times the square root of 3. And this will be my side length. And I know that the side lengths have to be the same, so they both have to be 2 times the square root of 3. I don't think I have an example on here. Let me check really quick. Oh, no, I do. Okay, I've got 2 more. So here on this next one, I've been given the hypotenuse. Now my hypotenuse is 3, so we should be moving to the short side first, which is this b value. I know that this is equal to the short side times 2. So if I divide by 2, I'll get my short side, which is b. So it looks like 3 divided by 2 is b. And you might go ahead and just call it 1.5 if you really like decimals, 1.5. I'm more of a fraction gal myself, but some people really like decimals. And now all I got to do to find the long side is take the short side, which I've said is 3/2, and multiply that by the square root of 3. So I end up with 3 times the square root of 3 all over 2. Or if you are calling that 1.5, you have 1.5 times the square root of 3. All right, the next one. So here I'm given the hypotenuse of 6. Remember, in my ratios, I'm going to draw that original. The hypotenuse is equal to the short side times the square root of 2. So if I had a square root of 2 there, it'd be really easy to pluck off what the side lengths are. But it's not going to be that easy. So I know that this 6 has to be equal to whatever this side length is times the square root of 2. So let's set those equal to one another and solve for the side length. To do that, I got to divide by the square root of 2. So I have x is equal to 6 divided by the square root of 2. So because 6 isn't underneath a radical, I'm not going to be able to just divide these two numbers, but I do have to rationalize the denominator, because to simplify this, I'm not supposed to have radicals in the denominator. So you probably remember doing this in Algebra 1 and Algebra 2. I'm essentially multiplying by 1 here. But when I do that, I'll end up with 6 times the square root of 2 in the numerator, and then the square root of 2 times the square root of 2 down here. I think we did this earlier in the lesson, is the square root of 4, and the square root of 4 is 2. Once I do that, now I can go ahead and simplify these two that are not under radicals. 6 divided by 2 is 3. And then I have times the square root of 2. So that's going to be the side length. And I know both of the sides have to have the same side length. So if x is 3 times the square root of 2, so is y. So hopefully you feel really comfortable at this point using those two special right triangles. Like I said, we're going to use them a lot. The next thing we're going to do is we are going to look at the 6 trigonometric functions. I am betting if you have made it through Algebra 2, you've probably seen sine, cosine, and tangent, and you may have seen cosecant, secant, and cotangent, but I'm positive most of you guys have probably seen sine, cosine, and tangent. So the first thing that's important is that we make sure we understand our definitions. When I'm defining the six trig functions, it's always in context of some angle measure. And so when I have this, I'm deciding that I'm going to use that acute angle. The opposite side is the one directly opposite from it. The adjacent side is the other side of the triangle. And it's adjacent because it's next to the angle. And the hypotenuse is always across from the 90-degree angle. So it's important that we understand when I'm looking at the angle measure that I know what's the opposite and what's the adjacent side. If you were to pretend this wasn't here, I wish I could get rid of it, but I can't. Just pretend that wasn't here, and let's pretend this is the angle I'm talking about. Well, then this is no longer the adjacent side for that angle measure. It's the opposite side. This is no longer the opposite side, it's now the adjacent side. The hypotenuse is always going to be the hypotenuse no matter what, because it's across from this 90-degree angle. So let's go ahead and define these. So let theta be an acute angle of a right triangle. The 6 trig functions of theta are defined as follows. Now the sine of angle theta, sometimes you'll see parentheses around the theta, is equal to the length of the opposite side over the length of the hypotenuse. I'm not going to write out length of, I'm just verbally going to say it. So it's length of the opposite side over length of the hypotenuse. Now CSC, this is cosecant. That's how we say this. It is the reciprocal of sine. It's hypotenuse over opposite, the length of the hypotenuse over the length of opposite. So notice sine and cosecant are reciprocals. Now cosine of theta is going to be the length of the adjacent side over the length of the hypotenuse, and secant is going to be the length of the hypotenuse over the length of the adjacent side. And notice cosine and secant are reciprocals of one another. And then the last one, tangent, is going to be opposite, length of the opposite side, over the length of the adjacent side. And the cotangent is going to be the reciprocal, length of the adjacent side over the length of the opposite side. So it's going to be important that you guys know these definitions. I am willing to bet you guys have probably heard of SOHCAHTOA. I feel like most of my students come in saying this catchphrase, SOHCAHTOA, and it helps them remember the sine, cosine, and tangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then for the new three trig functions, you need to know which ones are reciprocals of each other. All right. So the next question says, what is 1 divided by tangent equal to? If I were to have 1 divided by tangent of some angle, what is that equal to? Well, if tangent is equal to the length of the opposite side over the length of the adjacent side, then I have 1 divided by this fraction. Well, when I divide by the fraction, I'm really multiplying by the reciprocal, leaving me with adjacent over opposite. And one that is just cotangent of some theta. And so that's just another illustration to show that tangent and cotangent are reciprocals of one another. I would be able to say the opposite as well, that 1 over cotangent is going to be equal to tangent of theta. So I can see this illustrated right here in this trig identity, and I could also multiply by tangent and divide by cotangent on both sides and say 1 over cotangent is equal to tangent. All right, so the next question is, what about 1 divided by sine? Well, since you know you have reciprocals, if I have 1 divided by sine, I'm going to get cosecant of theta. And then what about cosine? What's 1 divided by cosine? Well, 1 divided by cosine should be the secant of theta. And so these are the first basic trig identities we're going to get, the reciprocal identities. And they're the first of many identities that you have, and depending on how far you go through the course, that depends on which ones you're going to work with. All right, so here we have a triangle, a right triangle, and I want to evaluate the 6 trig functions of the given angle. So here is my angle. So I have 24 is my opposite side. This 7 is my adjacent side. And I'm not given the hypotenuse, but I can solve for the hypotenuse using the Pythagorean theorem. So if I set this up, 7 squared plus 24 squared equals my hypotenuse squared. Well, 7 squared is 49. 24 squared is 576. When I add them together, I get 625. That feels like it's going to be perfect. So let's go ahead and take the square root of 625. And I do, I get 25. So here I have another Pythagorean triple, where I have 3 side lengths that are integers. Just a side note. So now when I'm doing sine, sine is going to be the opposite over the hypotenuse. So sine of the angle theta is 24 25ths, meaning cosecant is 25 24ths. Cosine is the adjacent over the hypotenuse, so I get 7 25ths. And then secant, therefore, is 25 sevenths. And tangent is going to be opposite over adjacent, so I get 24 sevenths. And cotangent is going to be 7 24ths. It's reciprocal. So now I should check and make sure nothing can be simplified here. They all look pretty good to me. So I now defined all 6 trig functions for that specific angle. Let's look at this next example. It says in a right triangle, theta is an acute angle, and cosine of theta is 7/10. What is sine of theta? So let's draw a right triangle. And I can set my theta anywhere. They say cosine is 7/10. So what they're giving me is that the adjacent side is 7 and the hypotenuse is 10. So they're saying, what is sine of theta? Well, to know sine of theta, I would need the opposite side over the hypotenuse. Well, I know the hypotenuse is 10, so we got to solve for the opposite side, and I'm going to have to use Pythagorean theorem to do that. Let's call it x. So I have 7 squared plus x squared equals 10 squared. 7 squared is 49, and 10 squared is 100. When I subtract the 49 from both sides, I get x squared equals a 51. And now when I take my square root, I get x is plus or minus the square root of 51. The square root of 51 doesn't simplify, and since I'm dealing with a side length, I know that this positive answer is the only one that is going to make sense. So I end up with square root of 51 over 10 as sine of that angle, theta. Why don't you go ahead and do this last problem on your own, pause the video, and then you can come back and check your answer when you're ready. Okay, so hopefully you drew a triangle. You have your adjacent side is 3 and your hypotenuse is 8. I asked you to find the cosecant here. The cosecant is hypotenuse over opposite, so you had to solve for that opposite side. When you do the Pythagorean theorem, you get the square root of 55. And so you're left with cosecant of that theta is 8 over the square root of 55. But hopefully you didn't stop here. We're not allowed to have radicals in the denominator. They're not simplified. So to rationalize the denominator, I need to multiply by the square root of 55 over the square root of 55. When I do that in my numerator, I get 8 times the square root of 55. And then the square root of 55 times the square root of 55 is just 55. I should check and see if 8 and 55 can simplify at all, but they can't. So there is my final simplified answer. So at this point, hopefully you feel really comfortable with that review of triangle stuff that you learned back in Algebra I and Geometry and Algebra II, and you are all set to do problem set 3.1.